So what I'm going to talk to you about this evening are two separate missions, the Cassini mission, which is ongoing, and then right at the end I'll talk to you about the Jupiter mission, which will be launched in 2022. One of the things that you find out when you work in planetary missions is you need a lot of patience, because from the time when you first start thinking about building instruments and sending a mission to a particular planet, it often takes 25 years before you start getting the data back. And it's really interesting for me to now be involved in the Jupiter mission and planning for things that will happen in the 2030s, when other people essentially did that on my behalf as far as the Cassini spacecraft is concerned. So this here shows you what I think is a really beautiful view of the planet Saturn. And one of the reasons I really like it is if you have a look just at the top here, you can actually see the edge of the planet through the rings. And that just underlines the fact that these rings are not solid objects. They consist of countless individual particles, each in their own orbit around Saturn. And what Saturn is it's made up of gas. That edge of the planet that you can see there is not solid. It's a large gas ball. Once you get down right into the interior, it's solid, and then there's liquid above that, and then what we're seeing at the edge there is a vast amount of gas. Now this is another view of Saturn which I really like because it shows the Earth and the Moon. You need really good eyes to be able to see it, but this is when Cassini was on one of its distant passages away from Saturn, and it was able to point back at Saturn, take an image of it in its entirety. There are a lot of moons in there that you can't see, but we have Mars in view, Venus as well, and then the Earth and the Moon are there too. And so it really gives you an idea about how big outer space is. Now, I thought I'd give you a little bit of history about Saturn. It was back in 1610 when Galileo, an Italian scientist, first viewed Saturn through a rather small telescope. And these were hand-drawn pictures that he drew of what he saw over a long period of time. And he couldn't understand what was going on because Saturn seemed to change shape. The first view that he saw, it was a planet, and it looked as though it had a moon on either side. And over subsequent weeks and months, it looked as if the moon was coalescing with the planet and then changing shape again. And it was only after quite a long time, 45 years effectively, when Huygens, another scientist, viewed Saturn through a much better telescope, that he realized that these weren't moons on either side of Saturn, but they were in fact rings. And the reason that they look different over time is that the inclination of Saturn changes. And so sometimes the rings, you can see them face on, and other times they're on the side and you can't see them at all. And so that's why Galileo and then Huygens found it really difficult to work out what was going on. And so this was the first view, or the sketch, that Huygens made of Saturn, where he proposed that it's essentially surrounded by what he thought was a solid ring. We now know it isn't solid. And it was a few years later that Cassini actually discovered that, and Cassini is another scientist, discovered that there's actually a large gap between the rings. And so it took some time for scientists to realize that Saturn was surrounded by these vast rings. Now, the Cassini spacecraft mission that I'm involved in is both a NASA and an ESA project. It was first devised back in the early 1980s. It was launched in 1997. It took 6.5 years to get to Saturn, and it's been in orbit since 2004. And I like to use this slide because it shows you all of the scientists and the engineers who are involved. If you're building a spacecraft as large as Cassini and as expensive, you really need to involve scientists from around the world to be able to not only be involved, but to get their governments to pay for it. Now, the instrument that I'm responsible for is the magnetometer. And this is an instrument that is placed on this very long boom, which sticks out from the side of the spacecraft. And what the magnetometer does is it measures the magnetic field in the environment that it's in. And the reason we put it on this very long boom is we want to get it as far away from the spacecraft as we can, so the magnetic field we measure is due to the space environment and not due to the spacecraft. This view here also shows this white umbrella shape up at the top. This is known as the high-gain antenna, and once a day for 8 hours, the high-gain antenna points at the Earth and sends data down to the Earth. And so every day for 8 hours, we get data back from the spacecraft. In addition to that, you can see that not only is the boom, but also the entire spacecraft is covered by a gold foil blanket. And that's to help keep the instruments in the spacecraft at a temperature that they can actually operate in. Because out at the orbit of Saturn, the temperature is about minus 150 degrees Celsius. And so you need to ensure that the spacecraft and the instruments can operate out there. This is a view of the Cassini spacecraft in a large test chamber before launch, and I like to show this for two different reasons. One of them is to give you an idea about how big the spacecraft is. Here are some people. They aren't small people, they're normal-sized people, standing here, so you can get an idea about how large the spacecraft is. And you can also very clearly see the gold foil. One thing that you'll notice that is different, though, is that long boom that I have my instrument on is not there. Well, it is. It's folded away in this little canister here, because if you think about it, you can't launch a spacecraft with a large boom sticking out from the side. And so what we did is this boom was deployed after launch, and it was deployed when we flew past the Earth. I'll show you the rather long trajectory that we took to actually get out to Saturn. One thing I wanted to point out about this high-gain antenna here is when we first went into orbit around Saturn, we actually came up from below the rings, and we were told there was this large gap between the rings, but we weren't sure whether it was completely clear. And so what we did is we came with the high-gain antenna pointing in the direction of travel, just in case there was anything in the way. And it's a good thing that we did, because there were some very energetic dust particles which have actually made holes in the high-gain antenna. And we'd much rather they made holes there than made them in any of the instruments. And then one last thing before I move on is this circular-shaped object is the Huygens probe. And some of you might remember when Cassini first went into orbit around Saturn, it dropped this probe and it traveled down through the atmosphere of Titan and one of the moons of Saturn, and it made observations on the surface as well. And it was this Huygens probe that was built by the European Space Agency, whereas the Cassini spacecraft was built by the US Space Agency. Now, there are 11 different instruments on board, and I'm only responsible for one of them. And so we need to, as a group of teams, work out who's going to make observations when, because we all want to move the spacecraft to be able to point in different directions. So you can't really talk about a spacecraft mission without showing a launch. And it was launched on the 15th of October, 1997, from Kennedy Space Center. And it was the first time I'd ever been to a launch, and it was really strange because it was way off in the distance, 2 or 3 miles away. And you could see the launch happening, and you could see all the sort of rocket firing in the distance. And then about 30 seconds later, the ground began to shake. And I actually had a colleague with me who was taking a video of the launch, and she wasn't expecting the ground to move. And so the video is jumping up and down because essentially the effect of the rocket fuel and the launch hit us. And so that was a very nerve-wracking time, because various rockets needed to fire to be able to get us to escape the gravity of the Earth. And so it was only about 12 hours later that we were certain that Cassini was on its way. So this is the interplanetary trajectory. This is the route that we need to take to get out to Saturn. We don't have rockets that are large enough to launch a spacecraft with enough fuel to get straight there. And so what we do is we fly past other bodies. And so what this is doing is this is a view looking down on the north pole of the sun. We have the orbit of Venus here. We have the Earth here. We have Jupiter's orbit here, and then we have Saturn here. And what we do is we fly close to some of the other planets. It's a little bit like a stationary billiard ball and a moving billiard ball. If the moving billiard ball bumps into the stationary one, it gives it a bit of energy. And that's exactly the same idea that we use when we fly a spacecraft close to a planet. We get close enough to its gravitational field that it gets a little bit of extra energy, and it moves it on. And so we actually had, let me see if I can remind myself, we had 2 flybys past Venus. We had a flyby past the Earth when we actually deployed our boom, and we took data so we could convince ourselves that we had calibrated our instrument properly. We had 1 final flyby at Jupiter, and then we reached Saturn in 2004. And all of those flybys took us 6.5 years to actually get there. So there's lots of science targets as far as a spacecraft mission as large as Cassini is concerned. I'm only going to focus briefly on 2 of them, but the 4 main targets are, we wanted to better understand Saturn and its rings. We're still not quite sure how the rings formed. And we also aren't quite sure of the internal planetary field at Saturn. Most large planets have an internal planetary field. The Earth does. If I had a compass needle, my brain's gone. The pointer on the compass needle will point at the North Pole. And that's exactly the same on Saturn. If you were able to stand on the surface of Saturn, the compass needle would point to the North Pole. And that's what my instrument measures, is it measures the magnetic field, and it allows us to work out how strong it is and how different it is from the Earth's. And so that was one of the focuses. The other one was Titan. Now Titan, not only has the Cassini spacecraft flown past Titan, I think it's about 110 times now, but it was also the Huygens probe traveled down through the atmosphere of Titan. And one of the reasons why we were so interested in going to Titan and focusing so much on Titan is that we think its atmosphere was very what the Earth's atmosphere was like when it first formed. So it's almost allowing us to go back in time and try and get an understanding about how Titan's atmosphere might evolve into the future, so potentially life might form on the surface of Titan. Now that we know more about Titan, we realize it's going to be a bit more difficult because there's liquid on the surface, but it's not water, it's ethane and methane, and so it's a very different beast. But we needed to get there to be able to find that out. And I'll show you a better image of this later, but you can actually see this blue haze around Titan. That's the atmosphere. And it's a very deep atmosphere. It's about 900 kilometers. And we have to be really careful when we fly close to Titan, because we don't want to get too deep into the atmosphere because it could cause the spacecraft to actually tumble. So we've got to be really careful. Another focus was all of the moons of Saturn. Every time a planetary mission goes to Saturn, it finds more moons. I think the count now is 63. I'm not going to talk about all 63, I promise. What I am going to do is I'm going to focus on one, and that's the one that you mentioned earlier. That was Enceladus, and that's because my instrument discovered an atmosphere on Enceladus, and I'm going to show you how we did that. And then the last topic which people have focused on is there's a big bubble that forms around Saturn, and it protects it from the effects of the incoming energetic particles from the sun. And that's called the magnetosphere. And I'm not going to talk about that at all. I'm just not going to have time. So, for you to be able to get an understanding about the data that we took and how we were able to discover the atmosphere, I just wanted to spend one slide telling you a little bit about what it is that we actually measure. And so that's an artist impression of the Earth with a bar magnet in the interior. I could put Saturn on that figure too. And this is the planetary dynamo field that's generated in the interior of a body. You can't see the field lines, those red lines, but you can measure them. But if you could see them, this is what they would look like. They start at one of the poles and they close at the other pole. It's a little bit like if you've got a piece of paper, you put a bar magnet under that piece of paper and you put iron filings on top of the piece of paper. What will happen is those iron filings will lie along the lines of force. And that's exactly what they would actually look like. And so with my instrument, you're able to measure these field lines, and you can tell if they're changing over time, and you can actually use them to work out how fast the planet is rotating too. And you might think, surely we know how fast Saturn is rotating? Well, it's quite embarrassing to say after, I don't even know how many years we've been in orbit, 1997 to 2000, quite a long time. We still don't know how long a day on Saturn is. And you might think, well, aren't we embarrassed by that? Well, yes, we are a little bit embarrassed. The reason that we don't know is because the surface of Saturn isn't solid. And we can't find anything on the surface that we can follow around and know that it's coming back every day. In addition to that, the magnetic field that we measure seems to be changing over time. And so we're unable to pin down what the rotation rate of Saturn is. The end of the mission will be in 2 years' time, and at that end of the mission we'll get really close, and we're hoping to be able to do that. The other thing I wanted to point out here is that Saturn and the Earth rotate on its axis. So if this is a field line, a single field line is going to rotate around Saturn once every day. And on Saturn, a day is about 10.5 hours. And so that's something else that I'd like you to keep in mind as I show you the data that we get. So let's talk a little bit about Enceladus then. This is a view that the Cassini imaging camera took of Enceladus as it was approaching. And they're two different images, and just so you can get a better idea of the surface. And the first thing that springs to mind is there are only a few craters. You can count maybe 10 craters in total. And in addition to that, the surface just looks young. There's some cracks on the surface, but it really looks quite young. And I'll come back to this slide. If you compare it to Mimas, which is a moon close by. So this view here shows you an artist impression of Saturn, all of the visible rings that you can see, and then where the different moons are as far as distance away from Saturn. So this is Mimas, this is Enceladus, here's a moon called Tethys, there's one called Dione, and then Titan that I mentioned to you is way off in the distance here. But as you can see, Enceladus and Mimas are reasonably close together as far as their orbital distance away from Saturn. But the surface of Mimas is covered in craters, absolutely covered. And so the implication is that something else is happening on Enceladus to help keep the surface looking young. In addition to that, the Voyager spacecraft, which were NASA spacecraft, which were launched in 1970s and got to Saturn in the late 70s, they had a single flyby past Enceladus. And one of the instruments on the Voyager spacecraft noticed that the surface was made up mainly of water ice. In addition to that, Enceladus is right in the center of another ring which we can't see, called the E ring. And it's a very diffuse ring. That's why we can't see it. But it's made up mainly of water. And so people had always thought, wonder whether Enceladus might be the source of the E ring, but there was no way in which they could work out how it could be. And so that was our knowledge as we went into the first flybys that the Cassini spacecraft made of Enceladus. And in 2005, there were three flybys in quick succession. There was one in February, one in March, and then a follow-on flyby in July. The first flyby was quite far away. It was about 1,300 kilometers away from the surface. And Enceladus is very small. It's got a diameter of 500 kilometers. And so this is what you would class a distant flyby. There was then a second flyby a month later, which was 500 kilometers away. And based on the observations that we made, we were able to persuade the Cassini project to take us really close on the third flyby. So the third flyby was 170 kilometers above the surface. And it was quite interesting, you know. Based on the observations that we made, I thought it was worth trying to persuade the project to take us really close. But we had spent the 6.5 years that it took us to get to Saturn to plan the first 4 years of observations. And we were always a little bit worried, what happened if we made a discovery? Could we change the observations? And we'd always been told that we could. But this was the first test. And I'll show you the data first, and then I'll tell you a little bit about how we managed to persuade them. So it's only magnetometer geeks that can get excited about data like this, but I'll try and pass over some of that excitement to you. If you think about it, the magnetic field that we're measuring is a vector. So it's in 3 dimensions. And so what we do is we measure the 3 components. And that's what you're seeing here. You're measuring the radial component of the field, so the field pointing away from Saturn. You're measuring the north-south component, and so if it's a field like Saturn, it's a dipole field, that's the dominant component, which you can see here. And then you're measuring the third component, which is the component that goes around the planet. And this is this component here. This is just the magnitude of the field. So all we do is we add all of these components together and we get the total field. And this here is 1 day's worth of data. And so for a geek like me that can look at this data and work out what's going on, I can tell you straight away that this was when we flew close to Saturn, and then we were moving away from Saturn. What I can also tell you is this data here, you can convince yourself it's got a wave on it. And that wave is telling you approximately what the rotation rate of the planet is. That wave has a period of 10.5 hours. And it's that wave that seems to change over time. That's why we can't pinpoint exactly what the rotation rate is. For those of you with very good eyesight or sitting very close to the front, you will notice there's a little pimple on the data, just there. There's also one in this component here too, but it's much more noticeable. There's something different happening in that component and this one here. And that's the flyby of Enceladus. We didn't expect to see anything at Enceladus because we thought Enceladus was a dead body. But instead we saw this large change in the field. To be able to try and understand what it was telling us, what we did is we subtracted the magnetic field of Saturn away so we could focus. Come on in. That's okay. You've missed lots of good stuff, but that's okay. So what we did is we subtracted the field due to Saturn so we can focus in just on what Enceladus was telling us. And so what I've done is, what we're doing is we're looking down on the north pole of Enceladus. This is the north pole coming out here. Saturn is way up to the top. The magnetic field lines and the plasma from Saturn are coming from the left. So remember I told you if this is the field line of Saturn, as Saturn is orbiting, the field line is orbiting as well. And if this is the moon, the field line is going to bang into the moon. And so the field lines are coming in from the left here. And this line shows you the trajectory of the spacecraft. Overlain on top of that line, I've put on little vectors which show you how the magnetic field due to Enceladus is changing. And what those vectors seem to be telling us is that they're almost seeing an obstacle that's bigger than the moon. There's something that's stopping those field lines from actually penetrating down onto the surface. So there's something that's in the way. In addition to that, I've made a note there's a large increase in wave activity. Let me just go back to this data here. If you have a look here, you can see there are lots of little wiggles on the data. And what that's telling you is there are lots of water group ions that are being picked up by the field. And so what we seem to be seeing is as we got close to Enceladus, the magnetic field from Saturn couldn't go down onto the surface. Something was stopping it. And in addition to that, there were lots more water group ions in the vicinity. So something was injecting water group ions. So this is what we thought was happening. So here you are, your eye's up above the north pole of Saturn and it's looking down on Saturn. The blue lines are the field lines of Saturn, and as I mentioned to you earlier, they're rotating around Saturn at a rate of 10.5 hours. And the little orange ball that's orbiting around Saturn is the moon Enceladus. If Enceladus was a dead body, the field lines, the blue lines, wouldn't see it at all, and they'd move straight through it. But instead, what we seem to be seeing, and now we're looking side on, what we saw instead that was these blue field lines coming from Saturn weren't able to move through Enceladus. They weren't even able to get down onto the surface. There was something that was stopping them from getting down onto the surface. And so we put a little schematic together to try and to help people visualize what we thought we were seeing. And what we thought we were seeing was that Enceladus has an atmosphere. the upper regions, just like the Earth has one, the upper regions of the atmosphere become ionized by the effects of solar radiation, and that stops the field lines from penetrating through. So they essentially act as a boundary. So what we did is we used data from both the first and the second flyby to put this together. And I went to the Cassini project. I actually went out to the Jet Propulsion Lab. And I was really fortunate. Before I met with the main project team, I happened to bump into the person who was responsible for the safety of the spacecraft. And he would have the final say about how close we could go. And I told him about what we thought we were seeing. And he said, "Oh, that's really cool. I've always wanted to go closer to a planetary moon than anyone else." And so I knew I had him on side even before I went and spoke to the rest of the project. But we had to convince them because it meant that some of the other instruments weren't able to take the data that they were actually planning to take. And we managed to convince them, but I must confess for 2 or 3 nights before that third flyby, I didn't sleep, because if we hadn't seen anything, no one would ever have believed anything I said again. But luckily, we did see something. And what we saw was very different. So this is what we thought was happening. There was this atmosphere covering the entire surface. On the third flyby, what we did is, as I mentioned, we were about 170 kilometers above the surface. What we did is we came up from below, and we flew like that. And it's amazing that we chose to do that, because this is what we found. Instead of the entire surface being covered by an atmosphere, it looked as if there was almost a cometary jet coming out from the South Pole. So there was this water vapor material spewing out from the South Pole. And so that's what our data was telling us, that instead of it covering the entire moon, it was focused just at the South Pole. But the interesting thing is on the earlier flyby, 3 or 4 months before that, we were so far away that if it had only been at the South Pole, we wouldn't have seen it. And so the implication is that the atmosphere is changing size and shape. But because we went so close, a lot of the other instruments were taking data as well. And so let me show you some of this data. So this is data from 2 different instruments. This is from the visual camera on board Cassini. And the first thing that you will notice are these blue cracks close to the South Pole, which the camera team called tiger stripe. This bottom left-hand image here shows you data from an instrument that remotely measures what the temperature of the surface is. And what they expected to see was that they expected the hottest region to be at the equator, because that's where the solar radiation is strongest. And what they found was that, yes, it was reasonably hot at the equator, but there was this hot spot right at the South Pole. Now, when I say hot spot, we're talking about 85 degrees Kelvin. And so it's quite low. I think 180 degrees Kelvin is about minus 100 degrees Celsius. So you can work out what 85 degrees Kelvin is. But out at Enceladus, this is pretty hot. And so what we did is we overlaid these temperatures on top of the visual image of the surface. And you can see that the hottest spot of 91 degrees Kelvin is lying right over one of those cracks. And so the implication was that this cometary plume, this atmosphere that was just focused at the South Pole, was coming out from the interior. And there was heat leaking out from the interior too. And this was a real surprise because, as I mentioned at the start, Enceladus is really small. It should have long ago cooled down from when it first formed. And so there's something else going on that's keeping the interior warm. This here is a view that was taken a few months later on a later flyby when the camera on board Cassini pointed back and looked at Enceladus, and you can see really the extent of this plume. The different colors denote the different densities of the plume. And so if you think about it, if the source is the surface, or underneath the surface rather, then it's going to be denser closer to the surface and it's going to move further away. This here shows a view of those cracks with the temperature along the cracks, and so you can clearly see the hottest part of the surface is the cracks, so the heat is coming up from underneath. And overlain on top of it are little stars. And these stars show you different source regions, and these sources change over time. So a region will open up on the surface where water vapor, and we now know organic material is leaking out from underneath, and then it'll close over again and it'll open up somewhere else. And just to give you an idea about the size here, this is 50 kilometers, so it gives you an idea. This is an extent of about 300 kilometers or so. This is some data which was taken by an instrument on the spacecraft called the Ion Neutral Mass Spectrometer. And this can only operate if it's flying through the plume, because what it does is it almost sort of tastes the air. And this is data that was taken on a very close flyby. I got all excited in 2005 when they took us 170 kilometers above the surface. We had a subsequent flyby which is 25 kilometers above the surface. And they'll never do it again because my mag boom began to wobble. So they're never going to go that close because they're really concerned that the spacecraft is going to tumble. But because we flew through the plume, what this instrument was able to do was able to measure all this different material. And you can see that there's methane in there. There's a lot of water vapor, which we knew anyway because my data showed that it was there. There's simple organic material. There's complex organic material as well. But in addition to that, and that's not shown on this view here because I think it was taken 2 or 3 flybys later, there's ammonia in the plume too. And that's really interesting because what ammonia does is out at the distance of Saturn, it acts as an antifreeze. And so if you've got ammonia in the material underneath the surface, it's going to enable water to stay liquid at very low temperatures. And you expect it to be liquid at about 176 degrees Kelvin, and we know that we've got temperatures greater than about 180 degrees Kelvin. So that's another bit of information as to why the water might be liquid underneath the surface. And so once we started getting this data back, everyone began to get really excited because one of the reasons we go to the outer planets is we want to try and understand if there's the potential for life somewhere else. And there are 4 things that you need for life to form. You need liquid water. We've got that at Enceladus. You'll need organic material, which we now know we have at Enceladus. You also need a heat source, which we know we have. And the 4th thing that you need is you need all of those 3 previous things to be stable over a period of time to allow something to actually happen. And that's what we're not sure about at Enceladus. We're not quite sure how stable this system is. Oh, I was about to press the wrong button. There we go. I think this is the last bit of data I wanted to show you on Enceladus. And this is a zoom in of one of the cracks. And the different colors, I can't see it quite so well from here. Go for it. I can't see quite so well from here, but if you have a look, the purple is cooler than the red, which is cooler than the yellow. And so you can see from that the yellow is essentially lying along, if you've got a big canyon, the yellow is lying along the edges of the canyon. And so it's really the sides of these cracks that are hottest. So yes, this was the temperature I was talking about. It's about 180 degrees Kelvin, which is minus 100 degrees Celsius, but compared to the rest of the environment, which is about minus 170 degrees Celsius, it's much warmer. So it's warm enough for liquid water to be the source. And also, if you go into these images and look really closely, it almost looks as though they're coated by some kind of material. So what could be happening is you've got these water vapor organic material plumes coming out from the South Pole, and some of the material is falling back down again. And so the last slide I wanted to show on this was the fact that this then led us to change the orbit that we did in the extended mission, and as we've had many more flybys of Enceladus. There have been lots of discussions about future spacecraft missions going to Enceladus, but to be able to understand an environment properly, you need to go into orbit. You need to be able to differentiate temporal features from spatial features. And Enceladus is very difficult to get into orbit around because it's so small. And so its gravitational field is very small. You need a huge amount of fuel to be able to get into orbit. But I think for me, the most positive aspect of this is it pulled all of the instrument teams together. I was about to say it forced us to work together. I don't mean it like that. It got us working together really well. We exchanged data, and that's the best way that you can find out the best about a system. So I'm keeping an eye on the time. I always take longer than I think, but I will speed up. I want to talk to you a little bit about Titan now. Titan is the largest moon in the solar system. It's about the same size as Mercury, and it has a dense atmosphere. And before the Cassini spacecraft got there, we had never been able to see down onto the surface. And the reason for that is that the surface is covered by this hydrocarbon haze. It's almost like a really bad smog in London if the traffic is bad and if the weather's just sitting there. We could never see down onto the surface. But the reason that we went there is we think the chemistry in the atmosphere is very similar to what our atmosphere was like when it first formed. So this was a view from the Voyager spacecraft, and you can clearly see that there's an atmosphere, and there seems to be some structure in that atmosphere too. It doesn't seem to be continuous. This is a view which was taken by the camera, and I showed you a smaller version of it earlier, really just to point out that it's an extremely thick atmosphere. I mentioned it's 900 kilometers in height, and we have to be really careful. We haven't been able to go closer than 900 kilometers to the surface because we're really concerned that the spacecraft will tumble if we do that. So there are a couple of things I wanted to point out about Titan. This is data which was taken by an instrument which looks at different wavelengths. And depending on the wavelength that it looks at different parts of the surface. And what it spotted was what it thinks is an ice volcano, which they call the snail. And let me actually show you a schematic of what they think the snail is, and the reason why they think it's an ice volcano. So I don't think it looks like a snail. I think it looks like a smiling fish. Don't you think it looks like an angelfish? But anyway, they called it the snail, so the snail it is. So what they think we're seeing here is that there was a large amount of ice which extruded out of the volcano and moved away. And you can see the effects of it. These are older parts of the material that came out, and this part here has been weathered away over time. But what they were able to do is actually able to get a 3D view of what this ice volcano looks like. Just to give you an idea, that's about 30 kilometers. So that extent there is about 60 kilometers in distance. So what they did is they put this cute little movie together, if I can find my mouse. There it is. To give you an idea about a 3D view and the height of the volcano. And I'll run it a couple of times just so you can see. But you can essentially see, this is that's where the material flowed out, and it would have flowed out in circles like this, and over time some of it would have worn away because of liquid on the surface and other regions didn't. But it gives you an idea of really the 3D extent. I think it's about 50 kilometers in height. And so finally we were able to start getting an idea about different features on the surface. The next thing I wanted to show you was what I call a virtual flyover of Titan. And this again is the same instrument data that I've just shown you. And what this shows you is really a composite of the surface. And what I want you to look out for is there are mountains which are 1.2 kilometers in height. There's a region where there are lots of lakes. It's known as the North Polar Lake country. At the South Pole, liquid has been discovered, but it's not liquid water, it's ethane and methane, so it's a very strange environment. There are vast sand dunes that crisscross parts of the region, and there's some flow structures as well. So let me play this, and you can have a look at it. The different colors denote height, and so blue is very low in height, yellow is a bit higher, and red is extremely high. And so this region here is the lake region, close to the pole. Then we have essentially mountain ranges here. We have some low regions, again some more lakes. This is the 1.2 kilometer mountain, and then these are the sand dunes that essentially fill the other sort of hemisphere. But the real surprise about Titan is we'd been in orbit for 6 years and we hadn't seen any liquid at all. And we knew that there had been liquid on the surface because when the Huygens probe traveled down through the atmosphere and took a sort of panoramic view of the surface and then landed on the surface, we saw features which were very similar to the kind of things you see on the Earth, which are only formed by liquid. But we hadn't seen any sort of sign of liquid at all other than the remnants of basins and things like that. We'd seen, there's the South Pole of Titan. We'd seen what looked like a lake, and it was named Ontario Lacus, but we didn't see any liquid in it. The first confirmation that we had that there was actually liquid on the surface of Titan was a glint from the sea. The sun reflected off the ocean and it glinted back at the spacecraft. And this happened 6 years after we got there. And it's because there's seasons on Titan. When we first got there, it was dry. There wasn't any liquid falling out of the clouds, but once we moved into the wet season on Titan, we then began to see liquid on the surface. And now we've got much better views of the different sources of liquid on the surface. But again, it's ethane and methane liquid. It isn't water. That's okay. Okay, so that was what I wanted to talk about on Cassini. In the last 5 minutes, I will talk a little bit about Jupiter. And this is a spacecraft mission called JUICE. It's a dreadful name. There's a bit of a history to the name. Should I tell it? Yes, I'll tell it. Okay. We first started talking about sending a mission to Jupiter with the US. And so the plan was that we would have 2 spacecraft. One would be built by the US and would go into orbit around one of the moons called Europa. The other would be built by Europe and would go into orbit around Ganymede. And I'll talk very briefly about why we want to go there in a sec. And so we had this fantastic mission planned, and then NASA withdrew. And the European Space Agency turned around to the study team that I was leading and said, you've got 3 months to plan a new mission with only a single spacecraft, and oh, by the way, you've got to change the name. And so we didn't have any time at all. And so we had a meeting where we met all day, and we then went to the pub afterwards and we had dinner. And we drank some gin and tonic because it had been a really long day. And we came up with 3 different names. The first one was Meow, which was never serious, but I thought it was quite cute. It was Moon Explorer of Ocean Worlds. And we thought we'd never be taken seriously if we used that name. So we then came up with a second name, which was Game, which was, I can't even remember now. Ganymede Moon Explorer, there we go. But it turns out that some other mission, failed mission, had been called Game X, and so we couldn't use that. And so the third name we came up with was JUICE, never thinking we'd actually use it. And that stands for Jupiter Icy Moon Explorer. Now that we've been selected and we're going to fly, people are saying to us, oh, you mustn't change the name, it's a lovely name. So I don't know, maybe it'll change, maybe it won't. But I've got quite a soft spot now for JUICE. Anyway, the reason we want to go to Jupiter is its moons have got liquid water underneath the surface. We know that. There was a spacecraft called Galileo, which spent 4 years orbiting around the Jupiter system, and they discovered fantastic things about the moons. And so this shows you a view of what the interior of 4 of the moons look like. Io, top left. Io is the one that's got sulfur volcanoes on the surface. Europa, which is the one that the US were going to go to, and now they've decided they also want to go. So they're going to try and get there the same time as us. And we know that Europa has a liquid ocean underneath the surface, and we think it might be in contact with the silicate mantle, and so there might be some material leaking out from the interior, which we might be able to see on the surface. Ganymede is my favorite, because I measure the magnetic field, and Ganymede has a planetary dynamo, just like we have. So if you stood on the surface of Ganymede, the compass needle would point at the North Pole. But in addition to that, it's got a liquid ocean underneath the surface. And what we can do is we can measure, with my instrument, measure the currents that are flowing in that ocean. And by measuring those currents, you can work out not only how deep the ocean is, but what the conductivity is, how much salt there is in it. And that gives you an understanding potentially how it formed. And then Callisto often gets forgotten about because it's not very interesting. The surface is very old, but we think there might also be water under the surface as well. So what we've done is we've got this mission which was selected 18 months ago by the European Space Agency to go to Jupiter and the moons. I was fortunate enough in having my instrument selected to fly on it. And this shows you an artist's impression of the spacecraft. We've now just recently had the spacecraft industrial contractor selected, and so soon we won't have to show an artist's impression, we can actually show the spacecraft. But one of the things you'll notice is that we're going to have large solar panels on JUICE, and so we're going to use power from the sun to drive the spacecraft. And so this shows you an artist's impression of Jupiter in the background. This is Ganymede, which we're going to focus on. We're going to fly by Europa twice. We're going to come up out of the equatorial plane and look down on the north pole of Jupiter and look at the northern and southern lights. We're going to fly past Callisto 10 times, and then we're actually going to go into orbit around Ganymede. And this is the first time ever that any spacecraft would have gone into orbit around a moon. I won't go into detail about the science that we're going to do, other than to say that the real focus is to try and understand whether there's the potential for habitability at these moons. I mentioned earlier there are 4 things you need for life. You need liquid water. We know we've got that at Jupiter. You need there to be organic material. That we're going to try and find out. You need there to be a heat source. We assume there's a heat source at these moons. Otherwise, if there wasn't, the water wouldn't be liquid. And you need it to be stable over time. So those are all the things that we want to try and find out when we get there. As far as my instrument is concerned, what we want to try and do is there are lots of things we want to do. We want to measure the induced currents that are flowing in the ocean, and that will allow us to work out the depth and the conductivity of the ocean. But we also want to try and work out what it looks like in the interior. We don't think it's ice all the way because we've measured currents flowing in the ocean before. But is there ice at the top and at the center, and there's only a small liquid ocean in between? Is there a very deep ocean? Those are the kind of things that we hope to find out. As far as my instrument is concerned, it's going to be like finding 3 needles in a very large haystack, because there are lots of different things going on. One of the things we want to measure is, assuming this is what the magnetic field looks like from Jupiter, as it changes, that's going to induce currents in this liquid ocean, and we want to measure those very tiny currents. But it's complicated by the fact that Ganymede has an internal field of its own, so we need to model that so we can subtract that effect away. And that's all embedded in the magnetic field of Jupiter. So there are 3 separate measurements that we need to try and eke out of the data. And it's so difficult, we've already started planning how we're going to do it, and we started to write the software that we need to do it. And I think that's my final slide. Yeah, it is. Thank you very much. No, because it's orbiting around Saturn. If something happened which knocked it out of its orbit, then potentially. But you know, there was that big hoo-ha about Pluto being a planet, and then it wasn't a planet. So I don't think so, because one of the things you need if you're going to be a planet is you need to be orbiting around the sun rather than around something else. I think the ones that we talked about today were part of the nebula from which Saturn formed. But I think where they've been in orbit around Saturn has changed over time. So I think there are lots of different ideas about why the interior of Enceladus is still warm. But one of the main ideas is it was probably in a non-circular orbit around Saturn. So it was in an elliptical orbit. So on part of the orbit it was really close, and on another part it was really far away. And so the tidal forces in the interior were really strong when it was close and less strong when it was further away. And so that kept the interior warm. Because if you compare Enceladus and Mimas, they're really quite close together and they look completely different. The original plan was, and this is what the instruments were built for, it would survive for 4 years. But then everything was going so well, the instruments were doing really well, and it cost so much to get a spacecraft out there that we were able to persuade NASA to extend it. And so it was extended for another 4 years to 2008. And then it was still going so well. So they've now extended it for the final time, and I promise it's the final time because we're about to run out of fuel. Well, I'm hoping we're not going to run out until September 2017 because it's going to be really cool. I don't know if I've got a... Can I find a... No, it's going to take too much time. What we're going to do... And a picture that'll show you where we're going to go. No, it's going to take too much time. Because I don't want you watching me trying to find it on my laptop. What we're going to do at the end of the mission is we're going to go really close. We're going to go inside of the rings. And we've only been inside of the rings once when we first got there. And when we went inside of the rings, the magnetic field we measured was different to what we've measured since of Saturn. And so the implication is that the rings are generating a field of their own. So what they've done is they planned the end of the mission, 17th of September 2017, to dive into the atmosphere of Saturn. But before it does that, it's going to do these very close flybys. And they've designed it with my instrument in mind so we can measure the internal field. But the person responsible for the spacecraft said we're going to be on fumes by then. So I don't know if we'll get there. It has uranium isotopes on board. And so it's, yeah. And some of you might remember when we had the Earth flyby in 1999 or something. There was a big thing made about it in the press because they were really concerned about the spacecraft flying through the Earth's atmosphere in case it crashed because it had all this radioisotopes on board. And so I had special press training to deal with those questions. It was in ceramic form.
Of course it's safe.
Yeah, of course it's safe, yeah. We wouldn't be allowed to fly today's instruments because they haven't been tested in space. And so there's this technology readiness level. Sorry?
That's not a health and safety issue.
No. Both NASA and ESA say that if you're going to fly a spacecraft on a mission that costs 1.6 billion euros, it's got to show that it's flown before. And so what we do is we test the instruments out on cheaper spacecraft. And you know, the way that we build them is they are redundant. Everything's redundant. And so I've actually got 2 instruments on Cassini. One of them stopped working. So I've now only got one left, but luckily, touch wood. I don't know if that's wood. And so one of the reasons that the spacecraft missions like these are so expensive is all the instruments have got levels of redundancy in them that ordinarily you wouldn't put in. And so, am I frustrated? A little maybe, but I'm getting excited about Jupiter. Because at Ganymede, the size of the field that we need to measure or eke out of the data is tiny compared to what we're doing at Saturn. And I got really excited, I mentioned to you earlier. It's clear I'm a geek. We had a face-to-face meeting with the spacecraft contractor last week. And we'd been saying to them for the last 5 years, we need a very long boom. We need to put our instrument on a 10 sort of meter boom to be able to get the observations. And they said, no, you'll get a 5 meter boom. So we had a meeting with the Prime last week, and they've given us a 10.6 meter boom. So we will be able to take the data. But it's a long, slow process, and you need to see the end game. You can't afford to get too frustrated. But you know, I'll be 68 when we get there. So I'm training some of the younger scientists on the team to potentially take over. Yeah, but I'll be so... No, but you know, I can see the sort of young guys on my team thinking, she's cranky now. What's she going to be like when she's 68? Tiny. Yes. Yes, yeah. It was dust particles, but tiny, tiny micron-sized dust particles. I don't know what the high-gain antenna is made of. Sorry. It should be easy enough to find out. But there are very tiny holes in it now. And so they did the right thing. You know, they said to us, oh, there's a gap of 7,000 kilometers, we'll be fine.
Would it be fair to say the particles are about the size of, say, the particles in cigarette smoke?
Yes.
Something of
Yes.
that.
But they were moving, you know, they were moving at incredible speeds. And so, yeah. But that was really nerve-wracking. That, just like the end of sort of mission is going to be, because we might be on the fumes by then. Yes, because it was essentially designed as a sun shield while we were, because we went to the inner part of the solar system and we flew past Venus twice to give us the kick to get out. And so we flew with the high-gain antenna pointing at the sun to protect the instruments. And it was a fixed antenna, because some of you might remember the Galileo spacecraft at Jupiter had an antenna that folded out and it got stuck halfway. And so half of the data didn't come back down. And so that's why they made this one a fixed one. Yeah. There's a small one as well in case this one fails. But so far, I don't have quite enough wood around me to... No. We're not quite sure when we'll burn up. It depends when the pressure of the atmosphere becomes really strong. But the plan is that as we're going in, we're going to be taking data. And so we're going to go in, I think, with the big high-gain antenna pointing inwards to protect us as long as possible. But there's a small medium-gain antenna that's pointing towards the Earth. And so they're going to be feeding data down to the Earth as we go. They tell me it'll work. They got us into orbit, so I'm not going to question them. But it's going to be really interesting to see if we do survive until 2017, because the data is going to be fantastic if we do. So I'm just hoping we have enough fuel to keep us going.